Hello everyone. So we would be discussing about FFT and the FFT resolution. So you all might have heard that FFT has a resolution of Fs by n. So we would discuss why does FFT have a resolution of Fs by n. So let's say you have a sine wave and you have, let's say, about 256 samples of the sine wave, and you wish to take a 256 point FFT, as you might have heard, because you have the samples with the length of 256. You have 256 samples, so you would take a 256 point FFT. Now what happens is, let's say the sine wave originally had a frequency of f naught. So it was sine 2 pi f naught t, and you sampled it at some sampling frequency, which is of course assumed to be greater than or equal to 2 f naught, and you got the 256 samples. And now you wish to estimate the frequency f naught by doing a FFT, which is a discrete Fourier transform. So what happens is, for FFT you have 0 to 2 pi frequency, because the digital frequency varies from minus pi to pi, or 0 to 2 pi for that matter, because the discrete time Fourier transform is 2 pi periodic, and the discrete Fourier transform is nothing but samples of the DTFT. So that is why the digital frequency varies from 0 to 2 pi. Now we have a relation between the digital frequency and the analog frequency as follows. We have the analog frequency equals the digital frequency times the sample time. So the analog frequency will be given by, basically, if this varies from 0 to 2 pi, what will happen is, this is the digital frequency, this is omega. So if we find the digital, this is in radians per second, if we find the digital frequency but in hertz, this is the digital frequency but in radians per second, if we find the digital frequency but in hertz, it will vary from 0 to 1 hertz, because it is omega by 2 pi. Now what happens is, since we have this relation, there will be a factor of Fs between the map from digital frequency to analog frequency. So let's say you have an analog frequency, and you want to convert between analog frequency to digital frequency, and both of them are in hertz, then you have a factor of Fs. So digital frequency between 0 to 1 will map to 0 to Fs for analog frequency in hertz. So if you want to go from digital to analog, you will multiply by Fs, and if you want to go from analog to digital, you will divide by Fs, because these two scales are equivalent, because these two scales are having a factor of 2 pi. So now, since we know this, we can get to the resolution. So what will happen is, you have n point FFT, and since in FFT you have e to the power j 2 pi k by n terms, what it means that for each value of k you are in a bin. And what I mean by bin, I'll specify it soon. What do I mean by a bin? So since the Fourier transform of this will be omega minus 2 pi by n times k, this will be impulses spaced by the value, that is delta k, which is 1. So the spacing between any two will be, where delta k is 1, it will be 2 pi by n. Okay, all these will be spaced by 2 pi by n. So if you recall this, if all these are spaced by 2 pi by n, which means that all this scale between 0 to 2 pi will be divided into n parts, where each part is 2 pi by n, since we have a n point FFT. So all this will be divided into n parts. So the resolution that we talk about, because the frequency is now quantized, it is no longer continuous, so the resolution will be the difference between, which is the least frequency that you can measure, that will be 2 pi by n. So this is in radians per second, and that too in the digital domain. If you use the same mapping that I described here between the digital to analog, you will map it to 1 over n hertz in digital domain, which will be fs over n, since you will multiply it by fs to get to the analog frequency, hertz in the analog domain. So the resolution came out to be fs by n, as I previously mentioned. So now we come back to the original product statement. We had a sinusoid at frequency f0, and we had 256 samples of it, and we took a 256 point FFT. So now what will happen is, you have the resolution of fs by n, and the input frequency was f0. So now what I mentioned here about bins, what is a bin? So as I mentioned, your 0 to 2 pi or 0 to fs for that matter is divided into intervals of fs by n. So what I mean by bin is, where does it fall? Okay, this is the first, this is the second, this is the third bin, this is the fourth bin, and so on and so forth. So there will be n or n plus 1 bins. You can get that, how many bins do we have, and your frequency will fall exactly into one of these bins when you do a FFT. But what will happen is, if you have a continuous frequency, let's say you have f0, so the bin will be f0 over fs by n. So let's say your fs by n was 10 hertz and your f0 was 100 hertz, then it will fall into the 10th bin of the 256 point FFT. Okay. So now what would happen when f0 by fs by n is not an integer? Okay, what will happen if f0 by fs by n is not an integer? Okay, let's say you had the f0 value as 11 hertz, and you had you had the value of fs by n as 10 hertz, and you had the value of f0 as, let's say, 22 hertz. So now what would happen is, when you calculate the value of the bin will come out to be 2.2, because what would happen is, this is 0, this is 10, this is 20, and this is 30. So now what would happen is, 2.2 will be somewhere in between this, because 22 hertz will be somewhere in between this. So when you try to get the FFT plot, it will look something like this. Because it cannot give you a peak here, because the frequency is discrete, you would see something like this. Your frequency plot will be kind of smudged over between these two intervals, and the peak will be close to 20 hertz. So what you will estimate is 20 hertz, and the estimation error in f will be 2 hertz, because your original f0 was 22 hertz. But the estimation error being an issue, the other issue is that in the frequency domain you will see smearing happening. This is what we term as smearing, which means that the FFT doesn't know which bin to put this into, the second bin or the third bin. So what it does is, it smudges the line between the two bins. 20 hertz will give you a sharp straight line here, 30 hertz will give you a sharp straight line here, but something that falls in between these two will sort of smudge out in between these two intervals. So the FFT plot will not look clean. That is the first issue. And the second issue will be, you will have some error in estimation of the frequency, because it will not fall exactly on top of these bins. So what you can do to minimize the delta f is, you can increase the resolution. You can increase the resolution either by increasing the value of the sampling frequency, or by increasing the number of points or the number of samples. Both of these are costly operations. Decrease the sampling frequency and increase the number of points. Both of these are costly because increasing the number of points increases complexity, decreasing the sampling frequency poses you at the risk of violating the Nyquist sampling criteria. So what you need to do is you need to increase the resolution so as to minimize the smearing as well as to minimize the delta F that is there. Thank you for watching.